All right. So let's start. The agenda for today, we have here four main items, or we're going to go over. Item number one would be what's new in ENERCALC. Item number two would be the prepared Q&A questions. Those are questions that were submitted to us over the past few days through email. So we picked a few of them to answer today and dig deeper. Item number three, optimized workflow of how to design steel beam, what the capabilities of that module, and then lastly, we will have the open forum for live Q&A, and I'll do my best to answer them. So, what's new in ENERCALC? And before we start digging into this, we have just a couple of housekeeping items that we need to go over. The first thing is, are you on the latest build of ENERCALC? Once you open the software, you will be able to see that on the very top you have the build number 2024-0409. That is the most recent build, and and once you do this, you'll be able to see this window. We want to make sure that you have this automatically checked for updates at program startup. This will be checked, so this way every time you open the program, if there is a new update, it will tell you so you can...
There's too much background noise.
Please, I cannot hear.
Have Mac turn off his microphone.
I think we need more people to just mute their computers.
Okay, can we wait until that's done before you proceed?
Okay, is that better?
You're feeding back somehow.
Yeah.
Okay, are we... is that better now?
That sounds much better.
All right. Thank you. So I just wanted to go over making sure that you have the latest build of the software on your computer. And to do this is very simple. You just click on the update icon, and then you will get this window. Make sure that you check this box. So this way, every time you open the software, it makes sure that if there's a new update, it'll tell you about it so you can have the latest and greatest. One item that's very important to note is that back in August, there was an issue with the automatic updater ability to the web updater ability to detect new updates. So this will require you, for those who are on this specific build, the 2023-0830, if you're stuck on this build, this is because it's not telling you that there's a newer version. However, would have been multiple updates since then. So this will require you to do an update manually one time only. You can do it through our website, which is enercalc.com/user, or you can do it directly from inside ENERCALC. And it's the same simple process. You click on update, and you click on this icon right here on this button, and that's the first step. You click on it, it'll take you to our website. You can see here this is the latest build that's available, and the first link is for a full installer, which you're not going to need that. This one is for the updater. You just click on this link right here. You'll be able to download it, and once you run it and you're good to go, it'll update to the latest and greatest, and then you can just repeat the same process to ensure that you're getting those notifications. So that is just the quick housekeeping item that we are covering today. The next thing that we're going to talk about is what's new in ENERCALC. And today I want to discuss bracing of columns. So I want to start with a quick engineering exercise, just a thought-provoking exercise to get you going a little bit. So if we have a column with girts framing into it from both sides, as you can see right here, then we apply loads. We have axial load, and of course we're going to have some lateral loads. So would you consider this column to be braced for Euler buckling, your axial force, your slenderness? Would you consider this to be bracing the column in the weak direction? Would you also, since this is taking lateral loads, what are your thoughts about lateral torsional buckling? Do you think this member right here is stiff enough, strong enough to provide, to act as a brace point for lateral torsional buckling? Or do you think that it doesn't provide that, and you want to maybe run your number on beam stability for the full length? So many engineers will have different approaches to this. Everybody will say something a little differently. Some will say this is too flimsy, this is too small, maybe it doesn't brace it or braces it. So everyone has a different take on this. And what we're trying to do here at ENERCALC is provide you with a greater level of flexibility so you can make those decisions based on the specific condition you have and based on your own engineering judgment. To put this in perspective a little bit, I want to go through a basic, quick example just to showcase what we're trying to do here. So a basic example that we have is just a simple column that's maybe that's 14 foot. That's the overall column height. We're going to go ahead and just assume it's pin, which is your typical condition for standard columns in buildings. And you jump all the way to the slenderness tab. This is what we're going to be discussing today. The slenderness tab will allow you to choose the type of bracing you have for your column, for Euler buckling. So the first part that I want to discuss is buckling about the x-axis, which is the strong axis of this column. And assuming that this brace or these girts, assuming that they're at mid-span, so 7 feet, and the full column is 14 feet. For the strong direction, which is buckling about the XX axis, if you want to say, hey, these girts don't help me, these girts don't give any bracing in that direction, you can simply just use the overall column height. However, if we jump to the buckling about the YY axis, which is the weak axis, if you think that these girts provide bracing for you, then you can say, okay, well, I'm going to go ahead and put this at 7 foot, which is the midspan where the girts are located, and you will be able to run your numbers based on that. Now, the new thing that this has already been there. The new part that I want to talk about today, or want to showcase, is the beam stability tab. And this talks a little bit about, since this is a beam column, it's getting lateral loads and it's also getting axial loads. So for lateral loads, now we want to make the determination if we want to run our numbers just based on an unbraced length, and this is for lateral torsional buckling. So for unbraced length, would I consider this girt or these girts to brace the column or not? And in this case, you can say, okay, I want to consider it to brace the column. Then you can put the new unbraced length, which is the 7 feet. Some other people might not like that, and they want to say, you know what, I want to run the beam stability analysis based on full column height. So this is just completely unsupported. I'm not going to consider that these girts are going to help me at all. Hence, you can just use 14. It is important to note that this is only for the unbraced length for lateral torsional buckling calculations. This is not for your bending calculations. So if you're calculating your moment, of course, you're calculating it based on the support conditions, which is the top and the bottom. So that's always going to be using the full height of the column. This is specifically for lateral torsional buckling. So again, in conclusion, when it comes to column bracing, this new feature allows the user to have a little bit more control regarding what they want to do and what fits their unique conditions. The second part of our presentation today is the prepared Q&A, and we've received a lot of questions to be covered, and we just had to pick a couple of them that we think are interesting. We answered pretty much almost all of the questions already, but these two questions that we selected because we think that provide some value. So the first question that we received is, does the cantilevered retaining wall module account for water tables? So this is a module that's been in ENERCALC for a long time. A lot of people are familiar with it. So I'm just going to jump here to the answer, and the answer is yes. You can input the water table height right here, as you can see it right from above the footing. Now, keep in mind, this model accounts for the water to be only on one side, which is the heel side. So if you have a condition where your water may be on two different sides, or you have something different, you might have to, or maybe just retaining water without any soil, you'd have to kind of look into this a little bit deeper and kind of exercise your engineering judgment. But overall, if you just have a water table, that gets accounted for, and you can see it here. Even in the 2D sketches, we graphically show it and say, okay, well, this area, that's where we have the water table, and would account for it. If you actually didn't have the water table, then of course this number will be a little bit smaller, and the whole graphic will look different. It'll just look all yellow, indicating that it's just one type of load. So that's one quick question we got. Another question we got that I think it's interesting is, does ENERCALC calculate the center of rigidity for a rigid diaphragm? And before I answer this question, I want to take a step back and introduce this module, because a lot of our users don't even know it exists. And if you click on the Add button here, and if you go to the Analysis tab, we have a module that's called Torsion Analysis of Rigid Diaphragm. And if you click on it, it has two primary tabs here on the left side. The first tab, it's dimensions and loads. And in this tab, you can put a lot of your, your applied load information, some dimensions. You can put your accidental torsion. You can apply the loads at various increments, different degrees. So you'll have a little bit more control here on the dimensions and the loads. And then the second tab, that is for the resisting elements. So in this case, you can just click on add here, and you want to add, maybe a shear wall, east shear wall, north shear wall, south shear wall, and all that stuff. The process is very self-explanatory. It's very easy. You can just kind of put a label so you know which wall is which. You can locate the center of the wall. So in this case, minus 40 and 10. This right here, the wall rotation, if we use 90 degrees, then that means it's parallel to the Y direction. You can choose the height. You can also choose the total length of the wall, in this case, 22 feet. And of course, you can choose the thickness of the wall. Once you build your various walls, assuming that you have, in this case, we have 4 different walls. You can see here, and I want to just stress this because it's important for the next slide. You have here minus 40 and 10. So if you go here, you will have a 3D representation of your walls, as well as a 2D representation, just to help you understand what you modeled. And this is the wall that we were modeling right here. It was minus 40 and 10, and that's kind of where you also can see it here in the 2D plan. And with that being said, we also have, this area right here. This is the datum that we use, which is the 0, point. So this wall, for example, which is the right wall, is 75 feet to the right, or to the positive X, and minus 10, which is the Y, which is the negative. So you can see everything being done from this datum. And now that we have all these shear walls located, and we have a good understanding of how to build that, I come back to answer the question, which is yes, the torsion analysis of rigid diaphragm module does indeed calculate the center of rigidity. You see here this red dot right here. This represents the center of rigidity of this rigid diaphragm. And as you can see, it's something positive in the X, and it's negative in the Y. And if you go in the software, you can see here datum to center of rigidity. You have 19.6 in the positive X and minus 3.6 in the which is negative Y direction. So that's kind of to answer that question. Jumping to the third part of our presentation, which is steel beam design. We're just going to go through a quick example, just a simple workflow of steel beam design. And that will be put in 3 simple steps. And then we have a quick verification example, which is a shorter version of the longer version verification example. And this uses, of course, AISC 360 2016, which is the 15th edition. So once you open ENERCALC, it's the same simple process. You go to add, and then you have here the tabs. All of your calculation modules are grouped by category. In this case, they're categorized under beams. So you can see wood beams, concrete beams, and everything. In our case, we want steel beams. So if you click on steel beam, that's pretty much your first step. Your second step is just fill in the information. Just go from one tab to another and fill in the information. You can put a simple description, pick your design methodology. Those are here standard values. You can change, of course, your FY and modular plasticity. And right here, that's when you put your compression edge lateral bracing. This is your lateral torsional bracing, and you can set it as completely braced. You can set it completely unbraced, or you can set increments. In this case, right now, we're going to assume that we have joist framing into our roof beam at 4 feet on center. Hence, I'm using spacing of 4 feet on center. Next step is simple. You just move on to the next tab, which is the beam span data. We have here 30 feet. That's just the length of the beam. I chose 14 by 26. You have here the full library, and you can use whatever size you desire. Now, I want to emphasize this part because I think it's a quick hidden tab right here, which is the properties. You can actually click on this tab, and you will get all of your section properties. So this way, you don't have to go and look them up in the AISC manual. This way, it's just a quick, if you're trying to figure out the exact depth or web thickness or something like that, you can just look it up right here. But moving on to this bottom portion here, that's the deflection ratios. Very standard for a roof member. L over 240 for total loads and L over 360 for transient loads. And you can put whatever deflection ratios you desire. Moving on to the next tab, which is span loads. You can click on add any load you want. You can from point load, full uniform load, partial uniform, trapezoidal. You can do a variety of loads here. In this case, again, just for the case of a quick example, you can put 20 live, 20 dead. If you choose a tributary width like I did here, then I can just put the tributary width, and I will put the loads here in KSF or PSF. In this case, 20 PSF live load, or live load and dead load, and I have 12 tributary width. Alternatively, if you know what your PLF is, you can just not enter any tributary width. You can just uncheck this portion here and put the load in PLF, whatever is easiest for you in your design. It's worth noting that loads on all tabs, on all spans, this tab right here specifically is useful whenever you have multiple spans. So if you have a multi-span beam and you have 20 live, 20 dead applied to all of the spans, you can just put it in this tab right here, insert the load or input the load in this tab, and it will automatically apply it to all spans. Unlike this tab where it applies the load per span. So if you have span number 1, span number 2, span number 3, you can control what load goes on what specific span. In this case, it's a single span, so these two are synonymous at this point. So with that being said, we just move on to the last tab that we're dealing with today in step number 2. That would be the load combinations tab. You can here select the load combination that you want to use, which is, in this case, I'm using IBC 2018. You can use an older version of the IBC or a newer version of the IBC. You also will have these 3 tabs. This is for we're designing ASD, so this is the strength load combinations. These are reaction load combinations, and these are deflection load combinations. You can actually adjust as needed. So for example, can actually use this right here in the deflection combination without, of course, affecting the strength combinations. You will have a great control, and this is applicable to all modules, of course. You have a great control over all of your load combinations. So you will get, you can add load combinations, you can delete some, you can copy them, you can edit them. And it's worth noting that you can have a bunch of them here, but then choose to only run a select few. So this part right here that says run and it says yes, if it says yes, then it's running. You can just say no and it won't run. Just one thing to be careful of is that if you go and click no on all of these, then you're not going to get any results because there are no loads applied on the beam. So at least you want to have one of these with a run, positive run. So this way you can actually have results. So with that being said, just kind of going from left to right, one tap at a time, you'll be able to fill in all the information that you need, and you'll be ready to move to step number 3. Step number 3 is simple, is just review the results and make sure that you're happy with them and they look good to you. So a quick green and red type of indicator, you can see here design okay or design not okay. In this case, it's okay because it's green and nice. You'll get information about your maximum bending stress ratios, your shear ratios, same thing with your deflection, and you get a quick synopsis here of your extreme reactions. This is just a summary of results. You can get a variety of different information as needed. For example, here in the bending stress ratios, you get to see here the maximum applied moment, and you get to see here the allowable moment right here, and it tells you also the load combination that controls this design. It is important to note that these are not, and I know a lot of engineers know this, but just we want to make sure that everybody is on the same page. These are maximum ratios, which means that they might or might not occur at the same spot. So in this case, the maximum bending is occurring in the middle because it's a simply supported beam, while the maximum shear is occurring at the support. So we're just reporting the maximum extreme values rather than corresponding values. I've noticed that this is a very useful thing that a lot of people are not aware of. If you click on the diagram and you pick the load combination that controls, for example, you will get this slide that'll give you the actual moment at that specific location. This is extremely useful if you're trying to design a splice, or if you have a beam that you're maybe butchering or reinforcing or something in a specific location and want to know, you want to sharpen your pencil and know exactly what kind of moment you're expecting in that location. Same thing for shear, or if you have specific deflection. So you can use just the slide rule, and in this case, at 15, you're getting the maximum moment, which makes sense. But you can slide it left to right to see what kind of information that you desire at a specific location. So very, very simple, very intuitive, and straightforward and easy module to use. The next portion of this is just a quick sanity check and kind of verification of a short version of a verification example. To remind you, we have our unbraced length being 4 feet. And we're just going to jump right here to the AISC table 310, which has the plots for the variety of beams and their capacities. So as you can see right here, we're using a 4 feet for unbraced length, and you can see here this is 96. You go up 97, 98, 99. This is the beam that we're using, which is 14 by 26. So you can tell roughly it's about 99.2. That's what I came up with, and it's kip feet. That's the capacity of the beam at that location. From our calculations, or from the software, it's 99.16. So you're good to go there. We can do a simple, quick shear capacity verification based on Chapter G of the specifications of AISC. And the equation here is very simple. It's 0.6 times Fy, yield strength of the beam, and the area of the web, and the shear strength coefficient. Since we're using an I-shaped, which is W beam, and it falls within the height to the thickness ratio that's required, we can actually use a lower, or a better omega factor. Instead of the standard 1.67, we get to use the 1.5. And of course, for this beam, the CV1 value is just 1. So at this point, it's a simple plug and chug, but the area of the web, that's what I was telling you about earlier. If you go to the properties tab, you can just get this instead of having to look it up in the manual on your own. So 13.9 times 0.255 will give us the area, the full area of the web that we need to use for the maximum shear or capacity calculation. And we have it right here, the allowable shear capacity. With, of course, the 1.5 omega factor, you get 70.89 kips, which is the same value as shown here in ENERCALC. So overall, ENERCALC's various modules, all of them are versatile, efficient, accurate, and of course, engineers can design with confidence using ENERCALC. With that being said, let's go to the fun part, and we will have here the live Q&A open forum where people can ask their questions. I'm gonna look at here.
Hey, Mac. I just wanted to chime in real quick on the Q&A. We do have actually a very large attendance today. Thank you everybody for being here. We have about 300 people in the room. So I have about partway through the session, I changed our admin settings so that everybody was muted just to take care of the echo that we were experiencing. And since we have such a large group, I would encourage you guys to go ahead and put your questions in the chat if you have questions, and then use the hand raise if you'd like to ask your question verbally. Just use the icon at the bottom of your screen to raise your hand, and I'll be going through kind of moderating these for Max so he doesn't have to multitask as we go through. So if you have questions, go ahead and put those in the chat, or if you've raised your hand, I'll be going through those one at a time and getting you unmuted so that you can pose your question to Mac. And Mac, go ahead if you had additional comments.
Yeah, no, I'm ready. I'm ready for the questions.
All right, so we have there's been a few things going on in the chat. We also have Chris Conrad and Derek Serino, who are both structural engineers on our engineering team, answering some questions in chat as well. We have a hand raise from David Torres. I'm going to get him unmuted here in just a second. Okay, David, go ahead if you want to go ahead and unmute and pose your question for Mac.
Do you have a question?
I'm not hearing anything yet. Okay, well, we'll go ahead and go to chat while we're working on that. And I'm just.
I know one of the questions that we received, we haven't answered that, but I'll go through and actually go through this. One of the questions that we received, and is Lutfi here on the presentation today with us?
He is in the house.
Okay, sounds good. So let me do this here, where I can pull up his question. So Lutfi was asking questions about the 2D frame, analysis module, and about the fixity conditions. And we have a few great resources that we can share with you here today, and then I will go actually. But the first part is that here in the help section, you can jump to the 2D frame, and you can see here we have information about joints and loads, and we also have information about members and member loads. Mainly, you can see here all of the joint information, what X and Y mean, and what Z means, and all of that. So this would be a good read. Another good resource for this is this right here, which is the ENERCALC frequently asked questions. If you see the 2D frame, you see assigning proper fixities, and this gives you a much better and robust idea of how to model fixities for a truss, fixity for a moment frame with fixed bases, and fixities with for a moment frame with pinned bases. So what I'm going to go through here, I'm going to go through a quick example of how to set this up. So if you click on the add icon here, and you go to analysis, and then you click the 2D frame. You'll get the wizard that's going to help you set up. You can do a variety of things here, including trusses, single bay, 3-member. You'll do a variety of things here, multi-story. In this case, to make this quick, we're just going to go to a single bay 3-member. And what I want you to know is that the question was based on Lutfi's question, and he wanted a fixed here, but then he wanted pinned bases. So the way that we're going to do this, first of all, we're going to click single bay 3-member. We're going to click next. I'm going to go just with generic numbers. The numbers actually that he gave me was 6 by 6. So I'm just going to use that. You can use whatever works for you. For us, a column section, I'm just going to use maybe a 4 by 4 by quarter. And for the member sections, the beam section here, I'm going to use a W14 by 13, just something simple. You can, again, choose whatever you need for your own specific conditions. So once you click on finish, it'll automatically generate this for you. You can just do this as you can do member analysis and design method. You can do ASD, LRFD, you do whatever you want. You can also here pick the sign convention. For us, positive Y is going to act downward. That's what I'm going to choose. If you want positive Y to act upward, you can just change that convention right there. So this is some good notes here that give you an idea of what you need to do. We have here auto calculate. You can actually turn this off if you don't want it to keep on recalculating. I like just to keep it on. It's simple. Jumping quickly here to joints and loads. It's very important that we have a good understanding of what X, Y, and Z actually mean. So X and Y, that's X and the left and right. Y, and let me put this here. So X and Y is just left and right.
Yeah, we have you now. Yeah, we lost you for a minute there. Yeah, that's about where we lost you. Yeah, it seems like, Mac, your audio is coming and going just a little bit. I'm not sure why. Yeah, I can hear you right now. It's coming and going. Some people are saying that they can hear me but can't hear you. Yeah, a lot of people are saying that they can hear you fine. Yeah. So just as a quick reminder to everybody who's in attendance right now, you have a setting in your upper right hand corner of your sessions window, should be near the upper right hand corner of your browser, where you can access audio settings, just to make sure that you have your output set to your headphones or to your speakers or whatever. And sometimes when you get into these meeting softwares, it'll change to a different unexpected output, like a display monitor or something like that. Right. Yeah, and there are some people saying that they can hear me but can't hear the main presenter. I'm not sure why. Yes, and some of the attendees can hear you as well. Yeah, and a lot of people say they can hear both. So, yes. Yeah, and for those who are having connection problems, yes, you can leave the session and close your browser and then rejoin the session using the link and see if that helps as well. And do make sure in your upper right hand corner that your audio settings are set properly to the output that you expect, whether that be your speakers, your headphones, etc. Yeah, sure.
So I'm gonna just go over this a little bit more. So the X direction, the Y direction, and the Z direction. This is just a 2D analysis. So the X direction is just left and right. The Y direction is up and down. The Z here is not meant to be a different axis. What it's meant to be is that it's the restraint for rotation. So if you have rotation, then if rotation is allowed, then Z is free. If rotation is not allowed, then Z is fixed. So what we're going to do, and what I think would be the best practice for something like this, since here at the bottom, we do have foundations. That means that you're honestly fixed in all directions because the foundation is not going to move. This is an important distinction because if we release the moment in the joint and then turn around and release the moment in the member, then you're going to have a stability problem. So the best practices for something like this, the first thing to do is to pick the first joint and joint number 4, which is these two joints, and make sure they're completely fixed. That's where you have your foundations. That's where you're really rigidly connected. And that's your external boundary condition. Now, joint number 2 and joint number 3, these two are free from a joint perspective. I'm going to go ahead and just apply a quick load so this way we can see what's happening. I'm going to apply a lateral load of 2.5 positive, which means going to the right direction. And sorry, I'm going to change this X right here. So it's in the X direction and it's 2.5 and it's applied to joint number 2. You can always click here to see the full frame sketch. And then it'll have here this giant red dot to tell you which joint you're looking at. So in our case, we're looking at joint number 2. So from this point, I want to jump to member loads. This is kind of where I want users to take advantage of this right here. It's important to understand what's happening in there as well, but also this is a very quick way of making sure that you have the right settings. So we fixed the bottom 2 joints and we made the top joints free. That means there's no external external fixity, or there's no foundation or something that's holding it in place. With that being said, those are the various members we have. I'm going to pick member A. Member A is actually pin at the bottom because we're trying to do a pin base. Pin at the bottom, which is the I, and then at the top, which is the J, we want that to be fixed. So the member is pinned at the bottom and fixed at the top. An easy way to do this, you can just click on this, pin in the I and fixed in the J. You click on that and you're good to go. If you want to examine this further, you can look here at the I condition, which is the bottom, fixed in the X, fixed in the Y, so it doesn't move in the X, doesn't move in the Y, but it's pinned in the Z. And what this really means is that it's saying that it's free to rotate. That means it's not a moment connection. You can change it if you want it to be fixed at the bottom, but in this case, we want a pinned based member, so that will be pinned. The top of the member, on the other hand, we want it to be fixed. So you can see here the top of the member, which is the J end of the member. It's fixed in the X, fixed in the Y, and the rotation is also not allowed. The rotation is restrained and fixed. If you look at the B member, the B member, which is the beam, we want the beam to be fixed in the I and fixed in the J. So at the end condition here by the I, and at the end condition by the J, and you can see it right here. It's fixed in all three directions, or the two directions and rotation. Lastly, we have the last member, which is member C. Member C, the I portion of it is fixed, but the J portion of it, we want it to be pinned. You can achieve this by saying, okay, this is going to be fix pinned, which you can just choose this, fix pinned, or you can come here and look at, as a sanity check, hey, the I end of it, which is the top in this case, is going to be fixed, 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 and the bottom portion of it is going to be fixed in the X and the Y, but it is free to rotate, and hence it's a pin condition. Once you kind of have all of this information, you can see here, you can apply some member loads, you can see the member forces, you can do a lot more with it, but for now, we just want to keep it simple so you can see what we're dealing with. Those here are the various section materials. I can always change the members right here, and maybe I want to change this member to something else. You can just go and pick it up from here. Load combinations, I'm just going to use maybe 2018. And then we look at the results. You can see here the variety of things. You have a lot of control. You can see a lot of your extreme joint displacement. So you can see the displacement in the X direction. You can see if there's any displacement in the Y direction. And then this right here is the reactions here on the right side. So you can see displacement, X, Y, Z, and then you can see reactions in the X, Y, and if there's, of course, any moment that you're dealing with. Lastly, you have here your stress checks for all these members. They seem to be working just fine. So what we engineers have to do always, whenever we're working with something like this, we have to see the deflected shape and see like, okay, this looks right or this doesn't look right, so we can have a better understanding of what we're doing and then go and adjust as needed. So in this case, we can magnify this a little bit more so we can see the deflected shape a little bit better. So you can see here, as I magnify this and see the deflected shape, you can see the bottom is allowed to rotate. And this is moving. This is your fixed right there, your moment restrained connection, but at the bottom, it's not moment restrained. If you want to go and play with this, I can go back to the members, and I'm going to pick member A to be fixed at the top and at the bottom. Let's just try it. So I can click here and I can click here. You can see that this is going to change to fixed automatically. Now, if you do this, you come back here to your shape and let's see, show the deformed shape. Now you can see, I'm going to make this super big just so you can see what we're dealing with. You see here at the bottom it is fixed, unlike earlier where it was allowed to rotate. Now it's not. So this at least graphically looks right. You can go and apply more loads. You can make this load bigger. I don't know, maybe I'm gonna use 7 kips, and if I make this load bigger, You can still see here the effect of, you can see the deformed shape right here. But if you go to the results, you can see that the stress ratios have gone up from 0.3 earlier to 0.6. So just a quick walkthrough of this module. And again, the two links that I shared with you guys earlier, which is this link right here and this link right here, the frequently asked questions, and as well as the user manual. They have great amount of information about this, and you can see exactly how to model a moment frame with pinned basis. You can just follow this right here, and it'll give you a great understanding of what you need to do.
Hey, Mac, just real quick while you have that page up, do you want to take a second to just hit the new ENERCALC.com and show everybody where to find some of that stuff on our latest edition of our website?
Okay.
So for those of you who haven't seen the latest ENERCALC website, there's a lot of resources that are really easy to find, more so than they used to be. And Mac's just going to walk you through that real quick, and then we'll get to a couple more questions.
And honestly, my favorite also is that if you have the software open, you can always just click on this help button, and it automatically brings this directly to you, so you can go through it and figure out exactly what you need to be looking at. So for example, calculation modules right here, analysis, the 2D frame, that will bring you to all of that. So this is a quick and easy way of reaching this, in case you don't want to go navigating through through the website. So this is right here. This is our new website. And you can see here for our user sections, this is the area earlier where I told you you can get a lot of those updates. You can install it completely new, or you can just click on the updater right here. And then as you go down, you'll see a lot of the documentation information. You can see the manuals right here. You can see it as an internet-based, and that's what I was using earlier. Or you can see it as a pop-up directly from your ENERCALC, and of course you can access it as a PDF, searchable PDF, so you can go and look at the variety of the things that it has as well. And this is also available for the ENERCALC for Revit portion, as well as the ENERCALC 3D portion as well. And you'll have a lot of good questions here. Ask questions, and always, if you have any questions, you can always ask them to the support@enercalc.com. And as well, the office hours program that we have here, we're going to be hosting this regularly. So keep your questions, keep on sending them to us, and we'll try to go through them and answer as many as we can, especially in a live and demonstrative format like we have today.
So Mac, the question we had from David earlier was regarding, he said the footing design module, which I assume is the general foundation design, talking about the 3D diagram, directionality of the loads, and that's, if you want to grab that module, we can walk through it. But and Chris will probably weigh in the chat as well. Chris Conrad's our director of engineering, who's here in the chat as well. And it's common in a lot of our 2D visualizations that we don't necessarily do reversal of those symbologies when signage is reversing. But feel free to go ahead and address. He wants to explain the sign convention for horizontal loads and moments as it relates to the controlling case for overturning. So,
okay, so we're going through just the general footing right here.
Yeah, he's just wanting a little more detail about the general foundation module, and specifically the 3D visualization and how it relates to reversing those load signage.
So, and that's the thing. So if we look, and just to make sure that I'm understanding the question correctly, so these two 3D little 3D diagrams have a really good idea of how the loads actually interact. You can look at, this is the PY, which is your axial load, and then if you have the VX, which that's the positive, so it's that direction. You'd have to a little bit orient yourself and orient your project or your specific case based on, you have to maybe draw it, or just make sure that you understand the loads, how they all apply. So for example, if I have a foundation that has axial load, and then we have maybe load in the X direction and load in this case, we're going to call it the Z direction. You want to make sure that those applications are in one, they're all together. The VX right here, as you can see, so this is the shear loads. And if I'm applying, let me do this right here. I think I'll have a bit. So if I'm applying 2 kips in this direction, I'm going to show everything. So you can see here a little bit of the loads that are being applied as well. So you would want to be a little bit consistent. So if you have something in the positive direction and then something in the negative direction, it doesn't have a full understanding of how the two will actually act at the same time. You'll just have to figure out the load. And Seth, you can kind of correct me if I'm wrong, but in this case, it doesn't look at positive and negative as 2 different directions. You'll just have to apply, if you have all the shear in one direction, then you just put that in one direction. So it wouldn't be, let me put this here. Let me try to get some of these off a little bit so we can apply the loads. Okay. Was that a question? Like if we have shear in both, like in the X,
Yeah,
but one of
so
them is positive and one of it is negative? Is that what it was?
Yeah, I
Right.
think the main question, I think he's talking about situations where you have
Hi,
both loads in different axes and loads in different directions, where you may go and reverse a sign. For example, if you're looking at a shear in one direction, then you want to reverse it and look at shear in the opposite direction, like a reversible wind lateral load or something like that. A lot of times in our 2D and 3D visualizations, you're not going to see an actual reversal of the arrow symbology in your sketch. Chris may have more thoughts to offer on that, but that's true of a lot of the different behaviors. For example, if you have upward versus downward load on your beam diagrams, positive X versus negative X load on your footing pedestals, that doesn't necessarily correlate to a real-time reversal of those arrow symbols in the sketch. And I think that was the primary question.
Hi, this is David Torres. I was able to fix my audio coming out of the meeting. And
yeah, but what I'm trying to assess here is that, like I got a question one time where there's a question about, for example, that was a little bit towards the steel beam module where they want to apply both downward loads and upward loads at the same time. And,
yeah,
whenever we're doing load
case,
reversal, we have to look at that differently. Each case a little bit differently.
Yes, I think in this case they weren't talking about multiple cases. They were just talking about manually reversing the signage on an inputted shear load and noticing that the arrow doesn't reverse.
I gotcha. Okay, so that makes sense.
Graphically.
I gotcha. Okay. Yeah, and I want to add here, whenever personally, whenever we have loads and moments acting on a foundation from 2 different directions. So for example, if we just have loads first of all, if we have an eccentric location of a column on a footing, and if we have loads acting, moments acting in the X and also acting in the Y, once we get into that, I always recommend people to start using the, simultaneously, I always tell people to start using the general footing by FEM, because it allows for a much greater flexibility in that regard. Because you see here, the load application eccentricity, you can, this module will only allow for eccentricity to be parallel to the X or the Z directions, but it doesn't allow for parallel to in the X and the Z direction at the same time. However, the other module, which is the one that's a little bit more, allows you more freedom, is the footing by FEM, which allows you to do a lot more with bidirectionality and, of course, eccentricities of the location of the column on the footing. And of course, you can have multiple pedestals on the footing as well.
Mac, just to point out one feature there, if you're in the general footing module, on the general tab, the very first one, the analysis and design setting has the option to do biaxial analysis. So when you toggle that one to yes, the options appear to be able to provide moments about both axes.
That's fantastic. Yeah, I always use just the other module. So yeah, this is good that you can actually do this from here, for sure. Yeah, there you go. You have all the information here. Seth, I think we are at the end of our 1 hour. We have about 3 more minutes. Is there a quick question that we can discuss in the next few minutes before we adjourn today?
Yeah, we have one more raised hand, and that's from Rita. Has a hand up right now. If you'd like to go ahead and unmute, you can go ahead and ask Mac your question now.
Yeah, hi. I actually have a question regarding, you have actually a point load analysis on a slab on grade. Do you happen to have a point load analysis on a two-way slab as well?
Not currently. At least not that I'm aware of. No, I don't. Not currently. We don't have anything for a point load on a two-way slab.
Okay.
Yeah, I think the intent of that module is just for a slab on grade.
Slab on grade, correct.
All right. Thank you.
Cool.
And
All right.
another thing is that a lot of the new features here at ENERCALC are developed by just feature requests. You know, the more demand we have for a specific feature, we try to kind of prioritize that based on the demand of our users and industry. So if you and if any of the other attendees that we have today find use for point load on a two-way slab, for example, if you guys can submit an email to support@enercalc.com for just a feature request, then we actually do keep track of all of this. This doesn't fall on deaf ears. We do keep track of this, and based on whatever gets the most requested, we make a serious effort to include it and grow in that direction.
All right. I'm not aware of any other outstanding questions. I know Chris and Derek did a great job of covering a lot of questions that were flying around in the chat. So thanks, guys, for taking care of that. We didn't take a second to introduce everyone, but we did have Chris Conrad, who's our Director of Engineering, was in attendance today. And then also Derek, who's another one of our senior structural engineers. And obviously Mac was presenting. So Mac, any final thoughts? I don't know if we scheduled as a monthly, but this is going to be a recurring event, like Max said. And definitely the main takeaway for everybody is stay in touch, send those technical questions to the engineering team, reach out whenever there's going to be office hours, send those to the office hours if you want to see them discussed. And Mac, you can go ahead and close with any final comments if you have a schedule for the next meeting. You could throw that out there as well.
Yes, I think one of my final comments, I think we have a little bit of feedback. Okay, thank you.
Go ahead.
Yeah, I think one of my final comments that I have, this is a new program that we're trying to get off the ground and get more people excited about, ask their questions, and again to provide this two-way, clean and easy communication line. We of course welcome all the feedback. Whenever you guys are done today, if you want to email us at officehours@enercalc.com if you have any, if you liked it, if you hated it, if you wanted it to be something different, if you have more questions. This is going to be an ongoing support effort where we're going to try to do this monthly. Based on the demand, we might do it a little bit more frequently than that. But yeah, we definitely welcome all of your feedback just on the overall structure, and we're dynamic enough that we're trying to present material that best benefit our users. So please shoot us your feedback. And with that, I think this is the conclusion for our first session today, and we hope to see you guys again soon. We're having this as scheduled on Wednesdays. So again, if that time is not a happy time for a lot of people, we can always work something out. And again, the frequency, I would like to hear back from our customers to tell us if once a month is frequent enough, if they want more, they want less. We're open to suggestions and we're flexible.
The last question, Mac, that I forgot to address was several people had asked if there would be recordings for the session, and I was going to let you cover what you would do with recordings for those who attended. I just wanted to reinforce the fact that we are hoping and designing this to be an in-person interactive event, and so for people who do not attend, there certainly would not be a recording available because it's not really a watch-on-demand thing. We really want to be able to interact with people, but I'll let you go ahead with your thoughts as far as whether the recording is available for attendees.
Absolutely, we're trying to make this as a dynamic and interactive as much as we can, and where we hear from you and you hear from us. The attendees probably will, for this session, you guys will have access to the recording, but it's not something that we were designed to be an on-demand, and it's not something that we're going to have a recording of for future events. Since especially that the interactive nature of it makes it very difficult to just sit down and watch it again. Especially it's not an intended purpose for it.
All right. Well, I think we'll go ahead and wrap it there. Thanks, Mac, for a great session. Thank you, everybody, for being here. And we will look forward to seeing you guys next month. And like Mac said, just want to reiterate, if there's any questions you didn't have addressed in this session, absolutely reach out to us via support@ENERCALC or office hours at enercalc.com, and we'll be happy to get those covered. So thank you, everybody, and we'll see you next month.
Thank you.